Hi, and welcome back. I'm Bill Westlake, and this is Lag Demon Programming. This video is the first in a series of videos that are going to cover some fundamental things about computer programming. It's not going to be a heavy-duty computer science course. It's going to be just some basic fundamental things that you really need to know if you're going to be a software developer. At any level, even for a hobby. And this first lesson is going to be on numbering systems. We're going to go over the decimal numbering system, then the binary numbering system, and then octal and hexadecimal. In future videos, we'll cover other very fundamental things about computer programming. These are going to be in a separate playlist as well, and I will have links to them from the main course. So thanks for watching, and I hope you enjoy the video. The first thing to understand is what a numbering system is. And so we're going to take a little bit of a quick look at decimal and review some of the things that you may have learned in grade school and high school, and maybe in other math courses you took. And this is just to catch up on what these things mean. So let's take a look at the decimal numbering system. So if we have a number like 9172, we know that this place here is the ones place. This place here is the tens place. This is the 100s place, and the 1000s place. All right? But where does that come from? Why do we say that that's the ones, the tens, the hundreds, and thousands? And why do we call this base 10? The reason we call it base 10, first of all, is because there are 10 symbols. And those symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. These symbols make up the base 10 system. There are 10 of them. And so each slot needs to represent 10 possible values. But they're 10 possible values multiplied by this base raised to a power. And that's how we get the 10, the 100, and the 1000. And that's because this first place is 10 to the 0th power. And then we have 10 to the first, 10 to the second, and 10 to the third, dot, 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 10 to the nth power. Well, for our purpose, any number raised to the 0th power is equal to 1. That didn't come out very good. That's 1. 10 to the first is 10. 10 squared is 100. 10 cubed is 1,000. All right? And then it keeps going up. The way our numbering system works is that it's really the sum of these individual digits multiplied by the position. So it's 2 times 10 to the 0th, plus 7 times 10 to the first, plus 1 times 10 to the second, plus 9 times 10 to the third. And that equals 9,172. All right? Let's go to a new page. What this means is that we can make up any numbering system. We can have a numbering system of base B to the 0th, and this is B to the 1st, and B to the 2nd, dot, 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 B to the N. Well, if the base 10 system has 10 symbols, and we want to create a base 2 system, we need 2 symbols, and we'll call those 0 and 1. So if we have a base 2 system, our base is 2 raised to the 0th, 2 raised to the 1st, 2 raised to the 2nd, 2 raised to the 3rd. 2 to the 0th is 1. 2 to the 1st is 2. 2 squared is 4. And 2 cubed is 8. So these positions have the values in decimal of 1, 2, 4, and 8. And so, following the same exact rules as we did in decimal, if we have the number 1, 0, 1, 0, that's 0 times 2 to the 0th, which is just 0, plus 1 times 2 to the 1st, which is 2, plus 0 times 2 to the 2nd, which is 0, and then 1 times 2 to the 3rd, which is 8. And if we add those all up, that binary number is equal to 10 in decimal. Just like we can count in decimal, when we get to 9, if we're counting 1, dot, 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 we get to 9, we carry 1 and put down 0 here in this place. And then we count again, 1, 1, 1, 2, dot, dot, dot. We get to 1, 9, and we have to carry again, making this one 2, 0, okay? The same thing happens in binary numbers. We carry, but we only have 2 symbols. So if we start off with a number, and I'm going to write all the digits for this one. If we start off with the number 0, and I'm not going to go through all of them, but the next number in line is 0, 0, 0, 1, but now we're out of digits. So we have to carry. So it's 0, 0, 1, 0. This is 0. This is 1. This is 2. The next number is 3, which is 0, 0, 1, 1. Let's check that. Is this 3? Well, it's 1 times 2 to the 0th, which is 1, plus 1 times 2 to the 1st, which is 2. 1 plus 2 is 3. Okay? And then we're out of digits again, and also we need to carry, which means we're out of digits here, so we need to carry again. So it's 0, 1, 0, 0, which is 4. And you can see that because it's 2 squared, which is 4. This is the 1's place, the 2's place, the 4's place, and the 8's place. So that's how binary numbers work. They count up just like any old regular number. The only difference is we only have 2 symbols. So we have to carry more often, and we move across. These values, 1, 2, 4, and 8, are just the conversion to the decimal system. All right. There is a reason why we use octal and hexadecimal. And that is because base 10 doesn't fit very well with binary. In binary, 9 is 1, 0, 0, 1. That's an 8 plus a 1. It's a 9. A 10 is 1, 0, 1, 0. So this is 9 and this is 10. The problem is that this last position, 9, doesn't fill up any group of bits. However, the number 7 does. If we know that these positions are 4, 2, and 1. 4, 2, and 1 add up to 7. So 1, 1, 1 is equal to 7. So if we use a base 7 system, we have 3 bits equaling our final number in that base numbering system. So if we have the digits, that we're going to constrain ourselves to using only the digits 0, 1, 2, 3, 4, 5, 6, and 7. And they are, very simply in binary, this. And I'm just going to list them out right here. This is the reason why we like octal. Every 3 bits in a pattern of bits is a single digit in octal. Let me show you how that works. If we have a number in binary 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1. Well, it's hard to visualize what that is. That's binary, and it's hard to understand what it is as a number. We can convert it to base 10, but to convert it to base 10, we have to go through and add and multiply and add and multiply and add and multiply to get those base 10 values. It's the only way to convert it. We got to add up all the bits. But there's a quick way to convert this to octal. And what I'm going to do is break this into groups of 3 bits. And I'm going to treat, even though it's one big number, I'm going to treat this as individual numbers and convert them into octal. 3 bits, this is a 7 in octal. 110 is a 6. 010 is a 2. 001 is a 1. And 101 is a 5. I didn't draw that 5 very good. 51267 is the octal representation of this binary value. That's easier for us to work with. It's also easier for us to work with bits if we're thinking in terms of octal. If I want to represent a particular bit pattern, because I know these very simple patterns. I know what 5 is, what 1 is, what 2 is, what 6 is, what 7 is. In fact, I just wrote them out. I know this whole pattern. If I need to set down a certain bit pattern, rather than typing out a whole bunch of 1s and 0s and trying to get that pattern right, I can think of it in groups of 3 bits, and I can put down the number 3, 1, 7, 6. And if I need to convert that to binary, I can do it like this. 6 is 1, 1, 0. 7 is 1, 1, 1. 1 is 0, 0, 1. And 3 is 0, 1, 1. I just converted that octal number into binary without doing any math whatsoever. And we can check it by dividing it into those 3 patterns. 110 is 4 plus 2 is 6. 111 is 4 plus 2 plus 1, which is 7. 001 is 1. And 011 is 2 plus 1, which is 3. 3176, they are equivalent. That's how octal works. When we write an octal number, typically we write it like this. It depends on the language, but a small o says that it's octal, and then we could do 3176. This is just a lowercase o, not a 0. This would be a 0, whereas this would be a lowercase o. And then 3176, and I'll show you that in code. In some cases, some things recognize octal. Some have a different way of doing it with a slant. And we'll talk about all that, or even a back slant. 3176 might designate an octal number. Just depends on the language. And we're not really talking about coding right here anyway. We're talking about numbers. So let's go to the next page, new page. Hexadecimal works the same way. The difference is we have more symbols, and I'll write them out here. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Now, this seems really strange right off the bat, right? How can a letter be a number? Well, it's very simple. We say it is. We need symbols, individual symbols, to represent a numbering system. By the very nature of the numbering system, you have to have individual symbols for each digit. And hexadecimal I-M-A-L, hexadecimal, this means 6, this means 10, it means 16. There are 16 digits here. 0 through 9 is 10 digits, and then 1, 2, 3, 4, 5, 6. These last letters represent digits in the hexadecimal system. In decimal, these numbers represent their decimal equivalent if they're alone. It's just their decimal equivalent, 0 through 9. A is equivalent to 10. B is equivalent to 11. 11. C is 12. D is 13. E is 14. And F is 15. So that we have 0 through 15 as symbols that we can put in place for this, which is 16 to the 0th, and 16 to the 1st, and 16 to the 2nd, and 16 to the 3rd. Okay? Now, why would we use this kind of numbering system? Well, again, it matches a bit pattern, and I'm going to explain in a moment for both octal and hexadecimal why they match those bit patterns. But for now, we can know something very simple, that a group of 4 bits in hexadecimal is equivalent to 1 digit written out in hexadecimal. So these are the places for the, well, actually these are the, I'm sorry, each of these places is some hexadecimal digit. We can have 1, we can have an A, we can have a 3, and we can have an F. We can have any of these symbols in this places, and this is 15. F is 15, we know that, times 16 to the 3rd. It's a big number. 16 to the 3rd is, I'll have to bring up my calculator. I don't know it off my top of my head. It's 16 times 16 times 16 times 15. It's a big number. 1, we can represent very large numbers in shorter numbers of digits, but also we can map directly to binary. Because in binary, if we have 4 places, we'll say a binary number 1101 is a number, and we know that this is 1, this is 2, this is 4, and this is 8. So if we add up the 1 spots, right? If we add up 1, 4, and 8, 8 and 4 is 12, and 1 is 13. 13 is a D. The single digit D can represent those 4 bits. So this hexadecimal number, F3A1, if we write down F3A1, F we know is 15. Well, guess what 15 is here? It's 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. Its F is all 4 digits are 1 in binary. We know what a 3 is. It's 0, 0, 1, 1. It's 2 plus 1 is 3. A is 10. That's 8 plus 0 plus 2 and 0 again. And 1 is just 0, 0, 0, 1. See how easy that was? I was able to convert this directly to binary. Converting decimal directly to binary is difficult on paper. It's very time consuming. And so I'm not even going to go through it because we don't ever do it. We can use the computer to convert decimal into binary. But we often are working with numbers and values that we have to go back and forth between something we can represent simply, like in hex, and have it represent some binary that we know what it's supposed to be. So if I need to represent some bits in certain patterns, I can represent them in hexadecimal. So when you see an address, it's usually written in hexadecimal, and in computer programming we use 0x FA37 would represent a hexadecimal number. Of course, there can be more digits. It can be 8216B can also be a hexadecimal number, and that's a big one. That's a lot of bits. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 4, 18, 36. That represents 36 bits, which is kind of an odd number. How many did I say? 1, 2, 3, 4, 5, 6, 7, 8, 9. CA B. So that's how we represent hexadecimal values. They're letters and numbers. They're actually numbers. The letters actually represent numbers. They represent the numbers 10 through 15 within the hexadecimal system. And they're easy to convert to binary, which is one of the reasons we use them. Now, why are they easy to convert to binary? Well, if we look at those binary numbers again, 2 to the 0th, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, these are called powers of 2. And they are 1, 2, 4, 8, and 2 to the 4th, excuse me, is 16. One, 2, 4, 8, 16. And you might notice also that these numerical values double as they go up. It's 2, so it's going to double for each frame, for each bit position. All right. Well, nowhere in here is 10. There isn't a place within binary in base 2 for 10, nor is there for 6 or 3. While you could create a numbering system in 3, it would not map easily to binary, nor would a bit numbering system base 5, 6, 7, 9, 10, 11, 12, 13, 14, or 15. None of those numbering systems would map easily to binary because they're not powers of 2. And you notice these two, 8 and 16, are exactly what we have. This is octal, and this is hex. And the reason they're chosen is because they're powers of 2. And because they're powers of 2, they directly relate back to binary. Now we could use, we already have a base 2 system, that is our system. We could have a base 4 system, but it's not terribly useful. Base 8 really is where it gets useful, and base 16. So if we had a base 4 system, it would be 0, 1, 2, and 3 would be our digits. So if we had a base 3 number like 1, 3, 2, it would map into 2 bits. Each one would be 2 bits. So this 2 would be 1, 0. This 3 would be 1, 1. And this 1 would be 0, 1. You see, it's a base 4 system. It does, in fact, map directly to bits. 3 is the highest possible number, and it completely fills 2 bits. So these map directly into binary, and that system turned into binary is that. And we can quickly find out what 132 in base 4 is by adding these up. This is 2 plus 4 plus 8 plus 16. It's 2 and 4 is 6. Plus 8 is 14. 14 and 16 is 30. Yeah, 14 and 16 is 30. So this actually represents the number 30. Let me double check that. 16 and 8 is 24, 28, 30. Yes, it is. I should have added it the other way. So 132 in base 4 is equal to 30 in decimal. So that's not very useful. It doesn't buy you very much with only 2 bits. 8 is not used as much. Octal is not used as much anymore as hex is. It's used in some applications in some areas, and we probably won't use it in anything that we're doing. What we will mostly be using is hex. And hex is extremely powerful because in a very couple of digits, like F, we can represent the number 255, which also happens to be a very important set of values. In binary, this is 1, 1, 1, 1, 1, 1, 1, 1. So remember that F is 15, which is 8 plus 4 plus 2 plus 1 is 15, and this is 15. This also happens to be 8 bits. And in most systems today, that's a byte, though that's not really entirely true by the definition of byte, and I'll explain that in a moment. What it really is an int 8 or a uint 8, either one, or just an 8-bit value that we often call an octet. The term octet definitely tells you it's an 8-bit value. The reason byte is not always entirely true is the term byte actually refers to the smallest possible grouping. Let me rewrite that. Byte. It's the smallest possible grouping of bits for the platform. So there are some platforms out there where the smallest possible grouping of bits is 16 or even 32 or 24. There are some embedded systems that use oddball numbers of bits like 12 or 18. In those cases, those also would be a byte. That would be the smallest possible representation of bits. On our Windows platform that we're working in, a byte is 8 bits. So we don't have to worry about what those weird platforms might do. So that's what binary, octal, and hex are all about, and why we use them. We use them because we can map numbers like F, A, D, C to binary as 1, 1, 1, 1, 1, 0, 1, 0. D is 13, which is going to be 8 plus 4 is 12 plus 1. And C is 12, which is 1, 1, 0, 0. All right, 8 plus 4 is 12. That is the binary representation of FADC. And you can, with a little bit of practice, you can learn to do this in your head just by remembering these very simple bit patterns. And the easiest way to do that is to write out the numbering system. Write it out. And remember that this is, oh, we forgot 0, 0, 0 up here. This is 0, this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which is also the 0 through 9, A, B, C, D, E, and F. So that's how hexadecimal works and why it's important in what we do in computers, because we can represent bits very easily in hexadecimal and know what those bit patterns are, and all you really have to do is learn that. If you learn this, and you can practice it just by writing it down, just like you did in grade school learning the decimal system. It's very easy to do, it's very easy to learn. Take a screenshot of this if you need to, and set it beside you, or print it out and write it by hand. That's the easiest way to do it. Or type it on your computer if you want to. But just go over it and learn it. Basically memorize it so that you can look at a D and say that's 1101. You can look at an E and say that's 1110. And you got hexadecimal down, but more importantly, you got that translation to binary and the binary back to hexadecimal, which is what you'll want to be working in, especially when you start working with bit patterns and various other things. So, thank you for watching. I hope you enjoyed the video. I hope you got something out of it. If you liked the video, hit that like button. If you really liked it, hit that subscribe button. And if you want to get notifications when I post videos, hit that notify button. And we'll see you in the next video. Thanks for watching.